All right, so we're going to continue on with lecture 7, fitting data's or models to data. So some of the things we're going to do for this section is going to be to define linear regression and understand the goals, results, and assumptions of that. We're going to compare and contrast linear regression and correlation. So again, talking about R and R squared values. Talk about models, parameters, variables. Look at linear regression and its applications. We'll also look at other varieties like nonlinear regressions. We'll look at multiple, logistic, and proportional hazard regression, all that kind of fun stuff that you might see out there in the medical literature. So first thing we'll look at is simple linear regression. So the goal here is to find the best fit line. So just like you mentioned previously, we're going to find the best fit line through a graph of data points. And so basically what we're saying is that based on a data set, we want to be able to generate a model to determine if a variable can predict another one, right? So if I can go back to that example of the insulin sensitivity and the lipid content, can I use that lipid content, if I were to just do a random muscle biopsy, and based on the model that I generate from that data, can I apply it to some other person and predict what their insulin sensitivity would be? Okay, so that's kind of what the linear regression is really looking to do. And so this is where we're going to have to determine both slope and intercept of that line that best fits the data, and this will give us our model that we can hopefully apply to other patients, right? So this is how we generalize it out from the data that we have to other people. So an example here is where we're talking about insulin sensitivity and that fraction of fatty acids. And again, this is where you really need to say which one is predicting which. In this case, because the fatty acid content had less variation in it, that's what the researchers were going with. So they said, okay, let's use this as our X, and we're going to see if this is going to be able to predict Y. So when we did that, basically to generate your formula for the line, you're going to see that the insulin sensitivity, or your Y value, equals your intercept plus your slope times that lipid content. So Y equals mx plus b, right? Everyone remember that from algebra, right? Hopefully. So anyway, so by using that standard equation, you're going to see that the model itself does not really account for random variation. It really only is going to be looking at the slope of that line, the intercept, and then how our x value is changing to predict y. We're going to see that there's a lot more complicated ways to generate these kind of predictions, and this is a kind of more simple example of a model that we can generate to help do this. And again, the goal is to find the values for the intercept and the slope that are most likely to be correct and quantify the imprecision within the confidence intervals that we looked at. And we'll see a picture of that in a graph in just a second. So again, linear regression finds the line that best predicts y from x. And then when we're doing this, you're going to be seeing that we're going to be considering the vertical distance of the points away from the line. That's going to be important because that's telling us the variation of where the values fall in a distance relationship to that line. So here's an example of the best fit line. The shaded area is a 95% confidence interval that was generated based on that data. Now you notice that not all of the points fit within the actual shaded area, and that's okay, but this is what the computers generate to be the best fit line. And notice here that the actual line, you're 95% sure that it's somewhere within this range, so it could go like this direction, could go in this direction, it can go lots of different directions, but it will fit within that line based on the data that we have. And now imagine if I had, say, 26 patients instead of 13, what would that shaded area do? Should get smaller, should get more narrow, because I'm going to have a better idea of where the actual best fit line for that data is going to be. So again, here you can see from again, this is typical kind of data spit out that you would get from statistical program. You can see here the slope that's generated there is 37.21. You can see as well that you're going to get an R squared value that's generated here. So anytime you're doing a linear regression, you're going to be getting an R squared value. We'll talk about what that means in just a little bit later. And so that's kind of the main points to take away from this without getting too much in the weeds. So again, the slope we got was 37.21 with that confidence interval going in either direction at 9.269. And so basically the best fit value of the slope is 37.2. And so basically what that means is that when you increase that fatty acid content by 1, whatever the integer is, you should see an expected increase in the insulin sensitivity of 37.2 milligrams per meter squared per minute. Okay, so that way you have kind of a prediction now that you can say that, okay, every time I bump up that point by 1 in the fatty acid content, I'm going to be able to increase insulin sensitivity by that much. Okay, so So you can see the confidence interval ranges pretty widely there, but does not include 0. So because of that, because again 0 would mean there's no correlation between the values at all. There's no way to predict x from or y from x. So it does not include 0. So we know that would be statistically significant line that we have there, right? Because again, the null hypothesis would be what in this case? Basically that you cannot predict insulin sensitivity from this fatty acid content, right? That's basically what the null hypothesis is going to be, that R squared value is going to be 0 basically, and you cannot be able to make any kind of prediction from there. So the other point to look at is the intercept. You see that the y-intercept when x is 0 is a negative number. And basically when you see negative numbers like that, obviously you can't have a negative insulin sensitivity. Basically it just kind of means that, even though I can predict values, kind of towards infinity in either direction, at a certain point physiologically it's not going to make sense anymore. So really you can't have a negative value there, so it kind of tells you physiologically it's really not possible. Okay, so again, as far as the graphical results, we saw that best fit regression line is defined by those values, and we have the shaded area showing us the 95% confidence interval there. And even though the only 6 of the 13 points are actually included within that area, that's okay because it's still, using all the points is how we generate that line in the first place. Obviously, there's less variability in the data. You'd see the points kind of getting closer, and as you got closer to, an R value of 1, it would be almost a straight line at that point. So this kind of shows you the range of lines you could have there, kind of similar to what I showed a little bit ago. Okay, so looking at the linear regression results, the other value that we saw, so we had the slope of our line, we had the y-intercept, we also are going to have our R squared value, right? So that's going to be looking at the coefficient of variation there. And so basically what this value is telling us, we have 0.59, and again, we know that can only be positive, only ranges from 0 to 1. Basically what it's telling us is that 59% of all the variation in insulin sensitivity can be attributed by that fatty acid content. Okay, so it's kind of the important point here is that R squared value kind of lets you know that while there is other things influencing the variation in the insulin sensitivity, we can say that 59% of it roughly is due to that change in the fatty acid content. Okay, so again, what would you rather have, a higher R squared value or lower? Because we said that our null hypothesis would be that there's no prediction that you can make from one to the other, so that R squared value would be 0 at that point, right? Showing there's no kind of correlation to the two. So closer to 1 is going to be better for us, right? So that way we can say that less and less of the variation is due to other factors. We can say almost all of it is due to this particular variable. So if you imagine if you were to look back at that example of I was giving increasing doses of lisinopril and looking at how blood pressure changed, you can imagine a much more cause and effect relationship to that. So you might imagine your R squared value would be much closer to 1 at that point, right? Because there's probably less variation. There's still some physical variation that patients would have, but for the most part you see a lot more kind of close because it's more chicken and egg versus here where we might not know if there's other factors or not, and we know that roughly 40% of it's going to be due to other factors that we have not accounted for. That makes sense? Yes.
Was there like a specific R where it says like you have to be above for it to be significant?
As long as it does not. So basically, the R squared value is generated from that R value, right? And so that can be significant. Yeah. So in this case, you're not really looking for a specific R value to tell you whether or not it's significant. You'll have basically like a p-value that will be generated with that to tell you whether or not it is. Yep. Okay, so again, the remaining 41% can be accounted for by other factors. Could be measurement areas, could be biological variation, could be lots of other things that could be affecting this. And here we end up seeing a p-value is generated at 0.0021, and so we know that the null hypothesis would be that there'd be no kind of relationship between the two variables. And so in this point, we're able to reject that null hypothesis and say, yes, we can have some prediction here. We know that these two are going to be related to one another. Okay, so very small possibilities just due to chance alone that we get these type of results. Okay, so again, correlation and linear regression are related. So we see some very similar things here. Again, the null for correlation is that there's no correlation whatsoever between the x and the y variables. The null hypothesis for the linear regression is that the basically horizontal line is correct, meaning that there's no, meaning that r squared value is 0, and you can't make any kind of predictions from one value to the other, right? Again, the two null hypotheses are essentially equivalent, so you can kind of think about them very similarly in your head. And then in this case, you'd actually see the p-values for both the linear regression and the correlation be the same. Okay, so again, these concepts are very similar, but just keep in mind that the linear regression is more about producing a model that allows for predictions, right? So I can take this data, and so since I know that 59% of this variation is due to the fatty acid content, I can go and generalize this out to potentially other patients. Okay, so the assumptions that we're going to be making when looking at these linear regressions is that the model is correct, hopefully. And again, not all relationships are linear. We're going to talk about non-linear regressions that do not follow this. And again, the linear regression equation defines a line that extends infinitely in both directions. So there shouldn't really be, again, just by using that line formula that we saw, the y equals mx plus b, that makes sense. And then for this point, for any value of x, you can the model can predict the y value. So that's kind of the assumption you're making when you produce that model, and that it works with the assumptions made that the relationship between x and y is linear within a defined range. So in this example, obviously, even though the line kind of goes infinitely, you can't have a negative value for insulin sensitivity. So that doesn't really make sense at that point. So really, you're kind of making the assumption that it works with this kind of biological area of possibility. The other assumptions you're going to be making is that the scatter of data around the line is going to be Gaussian. Again, assuming your data that you're pulling is normally distributed, that should be an okay assumption to make there. And that basically the variability should be pretty much the same throughout the entire set of data. Data points should be independent. Another important thing here, and that the x and y values are not intertwined. So that way that the you're not using x in order to calculate y, because then you can kind of be cheating at that point. It doesn't really tell you much. And then your x values need to be known precisely. So if there's any question about your measuring of the x value, that can call into question the results that you have. So you should be assuming that the stuff you measured is correct. Okay, so to compare the linear regression correlation, so with correlation, we're quantifying the degree the two variables are going to be related, right? Does not necessarily fit a line. We're just getting kind of a general trend of the data, and it will tell us the extent and the direction that one variable tends to change when the other one does. You don't have to think about cause and effect when doing a simple correlation, and it doesn't really matter which variable is x or y. In regression, though, you do need to think about cause and effect. You need to think about, okay, well, this change in fatty acid content is having an effect on the insulin sensitivity, based on whatever physiologic, reasoning you have behind that. You're thinking about cause and effect, and that you're trying to find the best line that predicts y values from changes in x. And so that's why you need to keep the x and y, the same throughout, and you cannot change those. That makes sense for you guys? Okay. So again, we're talking about linear. This is just a special meaning to describe the mathematical relationship between model parameters and the outcome. So again, our parameters were the change in the fatty acid content, with the outcome being change in the insulin sensitivity there. And then when we're talking about simple versus multiple linear regressions, basically simple is just saying that there's one x variable, whereas with multiple linear regression, you can have two or more x variables. And we'll talk about one of those a little bit later on in this slide set. Okay, so then we're going to be introducing the idea of models. We've kind of been alluding to those already when talking about these regressions. So some of the lingo here. So the goal of fitting a model is to try to find those best fit values on the parameter that helps to define it. So essentially, you're going to be starting with a data set. You can be generating these regressions so that you can make some predictions, and then you're going to fit that model to other data, or to use it in order to help predict that. So these models are really just a representation of something else, some sort of relationship between variables, whatever it happens to be. And typically, in order to create a model, it's much less expensive and more accessible and easier to do than actually having an experiment on thousands and thousands of patients. A lot easier if I can just take a sample of data, form a model, and then it can apply that out to other people, right? So it's either one equation or a set of equations to help to describe, represent, and approximate either these physical, chemical, or biological states or processes. And then they help us to design better experiments and help comprehend those results when we get those in future research. So typically these are kind of being done in small sample sizes, and then once you have that model, you can then apply it to larger sample sizes to make sure that it's validated, make sure that it works. A good example of this would be another bit of research I was involved with during my fellowship, where we were actually looking at evaluations of osmolar gaps and evaluating the effect that alcohol has on it. So essentially what we're doing is that when you are measuring osmolar gaps, you're looking for an unaccounted for measure of osmoles floating around in the blood, and so essentially you want to figure out what kind of effect the alcohol has on that and how you can actually back calculate to see what the actual alcohol content of the blood is using that. And so we do that frequently in tox patients who we think have maybe ingested toxic alcohols like ethylene glycol or methanol, something like that. And so very frequently these patients come in drunk as well, usually because they're depressed and they ingest alcohol along with some of these other toxic alcohols. And so the idea being is we want to accurately figure out, based on their serum osmolarity and their osmolar gap, how much alcohol they have in the blood versus some of the other stuff that may be floating around. Okay, so there's been lots of different values that people have used in order to help figure that out. Lots of different coefficients for alcohol. So what we wanted to do was to do this in an actual laboratory experiment where we took samples of patients' blood. We would measure the alcohol levels and then actually do the calculations ourselves and come up with a value that better describe that relationship between osmolar gap and the alcohol content. That make any sense? Anyway, we're trying to come up with a better value for this to let us have better predictions on which patients might have been exposed to a toxic alcohol. Okay, so this is an example where we made a model based on actual sample patients where we measured their alcohol content, and we're able to predict a model that gave us a much better variable for that. So just an example you might see where we are using models in order to help predict and help to generalize that out to other patients we can use that with. Okay. So again, regression helps to fit the model to the data that we have available, and then we're going to be adjusting the values of the parameters in the model in order to help make predictions of the model as close as possible to the actual data. So it's getting that best fit line that we can get there. So again, regression does not fit data to a model, but rather we're adjusting the model to help fit the data that we have. Another way to think about it, models are shoes and the data are feet, right? So you form the shoe around the foot instead of the other way around. Okay, so if we're going to be comparing models, actually I'm going to actually cut it here. We will continue with this tomorrow bright and early at 8 o'clock. Right? You guys complained about having it after lunch, so there you go, problem solved. All right, so I'll see you guys then. If you have any questions, let me know.